y. So this is much more general because the density can be a function varying with both variables. And so in that case, the mass of a two-dimensional region with a variable density would be the double integral over the region, and the corresponding x bar and y bar for the centroid, the x and y coordinates of the balance point would be, for x bar, it would be x, which is your lever arm measured from the y-axis. So this numerator integral is what you call the y-axis moment. So your x bar will be x, your variable density integrated over the region, divided by the mass, which would be this integral over the region. In the same way, y bar would be y times the density, and this numerator would be the moment relative to the x-axis. And again, your y bar would be this moment divided by the mass. If you had a three-dimensional solid, so I'm using the letter D for the region over which you'd, or throughout which really you'd be integrating the domain, then the mass would be what you compute, allowing for a density which might vary with all three variables, and that would be a triple integral. And in the same way, the x bar, y bar, and z bar, because you have three variables, so you'd have three coordinates for your balance point. The handy way, I think, to remember things if you're working with double and triple integrals, whichever letter it is with the bar on it, for your moment, you have that same letter and then your density, and you're integrating now throughout the volume and dividing by the mass. And you do the same with the y bar and the same with the z bar. So these, once you have the concept, say, of the function of two variables, comparing what we can do here with what we had to do in chapter 6, this is a good deal easier, because if you think about the y bar, which is your moment, which involves your moment relative to the x-axis, the way we had to do it in chapter 6, we had to express the lever arm distance, the y, in terms of x, because x was our only variable. So we had to take that, think of vertical strips and take the average height. Top curve was f and lower curve was g, and we had to take for our lever arm distance relative to the x-axis, the average, which would be f plus g over 2, and then times by the height of the strip, and you got the formula with a half and the difference of squares, top curve minus bottom curve. If you can think back to how you did things in chapter 6, of course that was last semester, so maybe you don't remember it, but this is a lot cleaner, certainly. I think enough so that I'm not sure, I think maybe it would be better not to even talk about the center of mass stuff in Math 175 and wait till you have a more efficient integral. However, the other side of that is a lot of students never take third semester. So these books are a compromise, of course. Everything's a compromise. It's the same. Well, I'll get it for you. I know. Now, the moment of inertia is a very important concept in building. if you notice my high-priced mathematical models here, everybody knows if you're building something, you're going to support a floor or people or anything, you turn the thing this way and you don't turn it that way, right, as far as strength. But it is the same truss. So the question is, why is it that they go this way? And, well, that's the answer is what's called the moment of inertia. And so when you take in engineering, if you're in engineering, if you take the properties of materials, I think that's what they call it now. It's a course that was called Strength of Materials years and years ago when I took it at Berkeley, and I think it's also been called Mechanics of Materials, so on. But anyway, you get into the concepts now that we're going to address, and then we'll see how you actually do the moment of inertia problems with the calculus over here. So, say you're thinking of a two-dimensional cross-section or plate. So, if you're thinking of a beam, or, well, this would be a truss like this, what you really care about is if you have an axis, like I have the stick, computing the moment of inertia, as it's called, of this cross-section as an area. Okay, and that goes with the handout that I gave you. So, if you're thinking of the moment of inertia then about the x-axis, that is defined as the double integral of the variable density, if you have a variable density, then the squared distance from the axis to each point in this region, or what would be the cross section. So if you were going to compute the moment of inertia, if the stick is the x-axis, you're talking about using the squared distance from the axis down here to each little point that's in this cross-sectional area. And you would take into account the density. Of course, if it's uniform material, it's just a constant, but you're still, so what you're really integrating is the squared distance to each point. Notice if you have a thing like this, you have to break this into three problems because you've got a rectangular cross-section down here, then you have this rectangle, and then you have another cross-section up here that's like that. But the integral, the contribution to the integral from this cross-section is by far the largest contribution because you're doing the squared distance as a multiplier, and the squared distance from between my hands is certainly a lot more up here than down here. Okay, so this is also called the second moment because you're multiplying by y square, whereas if you were just doing center of mass, then this multiplier is first power, and you call that the first moment. The moment of inertia or second moment concept is important, not just in building and design like that, and in general in machine shop design. It's also important in statistics. If you take the Math 360 course, for example, next semester, they talk there about what they call moment generating functions, and we can't go into that in this class except to say that the calculation is the same type of integral, an integration of a square over a region. A multiplier that is squared, integrated over a region. So you can define for a two-dimensional cross-section the moment of inertia relative to the x-axis or the y-axis or the origin, which is what you call the polar moment of inertia. So you'd use the polar moment of inertia if you think of a wheel that's mounted on an axle, and you're talking about the moment of inertia around what would be like the pole of polar coordinates, where the wheel is actually on the axle. And that would apply, say, to the flywheel on an engine, which has a moment of inertia. When you have it going, the inertia makes it want to keep going, and that's how you keep the engine running smoothly. And it's also a resistance you have to overcome to get it to go to start with. So your polar moment of inertia is actually the sum of these two. It's the density times x squared plus y squared, which of course is r squared in polar coordinates. So commonly, if it's a polar moment problem, you would change to polar coordinates and do your integral that way. You can also have moment of inertia for three-dimensional solids relative to the x-axis, y-axis, or z-axis, and the formulas look like this. I don't have any of the homework problems that really require doing this, but these formulas will work with these, but you can certainly get that. So as I started saying with the polar moment of inertia, if you think of a wheel that's mounted on an axle in terms of the polar moment of inertia, capital letter I for inertia and the subscript O for the origin or pole, when the wheel is not in motion, when it's at rest, then that I sub 0 measures that extra force that you need to apply to get it to move. And that's more than to keep it going once it's going. And that's what I'm saying here. Then when it is in motion, that measures the force that you have to apply to get the thing to stop. And so it's something you have to overcome when either getting something to go that isn't going or to get something to stop that is going, because it's a measure of the reluctance of the wheel to start turning or its desire to keep going if it is going. And you've all seen this one way or another by observation. For example, if you have a grinder or something like that where the wheel is going, you switch off the power, but it'll still keep going a little bit, depending on how the machine's designed. So in terms of bending beams then, which gets back to the truss on the table, say you have your cross section and you have an axis of symmetry of the original cross section, and then you put a load on your beam or truss, and it has to bend even though it may be very slight. We don't usually think of a floor with a real sag in it that you notice, but there is certainly some. So it bends into what Euler called the elastic curve. The elastic curve is the solution to a differential equation, which involves the moment of inertia of the cross-section. And also it involves another constant, which is called Young's modulus. The E, the Young's modulus, is related to what kind of material it is, and it's something that you determine by experiment. If you take that properties of materials course, the lab part of it consists of taking various pieces of various kinds of lumber, blocks of lumber, and putting them in a press, seeing how many pounds per square inch you need to make it fail, and stuff like that. And the Young's modulus is measuring that kind of thing. So the differential equation then is that the product of Young's modulus and this moment of inertia, then that product has a name. Euler named this product and called it flexural rigidity. And so you have the constant here times the fourth derivative of the y, which would be the y for the elastic curve. I've exaggerated, of course, how much the sag would be so that it's easy to see, but hopefully you're not going to buy a house where there's that much sag in the floor. Anyway, then this would be a function that's how the beam is loaded. And so you'd have to make an assumption about this or have some way to know from experiment. When you're solving a fourth order differential equation like this, you see you're going to integrate 4 separate times. The first time you integrate, you get the third derivative, and that'll be the integral of this, and so on. So you'll get a constant of integration each time. So there'll be 4 constants of integration by the time you get to y. So that means you have to consider your boundary conditions to get these constants. So if you had a uniform load, for example, and length L, then it matters how you're supporting the beam at the ends. That's where you get your constants, your information for your constants of integration. So if you suppose it's clamped or embedded at both ends, the ends are where x is 0 and x is L, then if it's clamped at both ends, then y of 0 and y prime of 0 and y of L and y prime of L are all 0. You can certainly have other kinds of boundary conditions, but if you happen to use those to make something that's easy to solve, you get a solution for your elastic curve, which where I'm assuming a uniform load, so the W is constant and the E and I are constant, and so it'll look like this, where Y is positive down. So notice that the solution says that as your flexural rigidity here increases, then the sag decreases because you're dividing by it. So the bigger the denominator here, the smaller the quotient, and so it means the smaller the amount of sag. So the strength then, in terms of reducing how much the support sags under load, is proportional to what is your moment of inertia. Your E depends on what the material is, and if you're using that kind of material, that's what you're stuck with. But what you can vary is your moment of inertia, depending on what choice you make. So, for example, what makes the difference here, see, these are all made of the same kind of stuff that people use now. You call this stuff oriented strand board. And you can see what it is. It's chips in the mill put together with glue that people have developed now that binds this. It's very much stronger than you think it would be. I mean, it looks like it's junk, and carpenters of 100 years ago would certainly have said so. They used to burn this, but this is what you get now. And these, if you look closely, are laminated. They're thin strips laminated together. You call this laminated veneer lumber, LVL. And the binding in the glue that's binding these strips together is stronger than the natural wood would be from the tree if you just cut it as dimension lumber. So, you see, this has a considerably bigger cross-section on this upper rail than this does, and this one is a bigger cross-section than this is. Turn this one the other way. And also, of course, this is taller, and that's taller than that. And, well, I guess it isn't taller, it's just that it's the bigger rail, top and bottom. And this one is taller, and also this rail is bigger stuff than this. Well, what makes most of the difference in the computation of the moment of inertia of the cross-section, where this one is quite a bit bigger number than this, and this is quite a bit more than that, is actually the size of this upper rail, because you're multiplying y squared times all the little areas here, and the same here and there. So this is 5,000, this is rated at 5,000 pounds load, and this is 3, and this is 2. So what you find is that compared with dimension lumber that would be comparable height and width to the rail, these have about as much strength, and because of the very comparable moments of inertia, and they cost a lot less money than the corresponding dimension lumber would be if you can even get it, which is hard to do, especially that bigger one, because the trees now just aren't that big mostly. And also, they're a good deal lighter because you have a good deal less material there. So anyway, I've written down here what I've been just been saying, and in the same way, if you're working with steel, where people would use trusses like that, say I-beams, you can reduce the weight, and of course you can reduce it further with steel if you use high-strength steel and so on. So then the question is, let's look at some computations. So look at your handout. A second. So you can see my sketch is similar to the model. So if you're looking at the cross-section for a joist to replace 2x10 dimension lumber, although your moment of inertia is really a double integral, if you have uniform material, which you would certainly assume any of these would be, then what you really care about in your moment of inertia is the squared distance from this axis down here going this way. You don't really, your contribution from integrating with respect to x, if you think up and down is y and this way is x, is just simply to get the area. So you can do the problem, you can simplify your double integral when it's uniform material by just saying, well, it's the area times the integral of the squared distance measured vertically. So that's lets me work the thing as a single integral. What you have to do is break this into three parts, because you have this area, and then you have the oriented strand board area, and then you have this one. So you see in my sketch, I have the dimensions. I think the dimensions maybe actually go with this one, but it's one of those anyway. So you have the 1.5 inch square. I'm not sure now, without taking a ruler here, which one of the three that is. And then you have the center part, and then you have the square or rectangular cross section again up on the top. I think it's actually this one. And if you assume that it's all uniform material, which may not be true. I mean, the strand board is a different mix than the veneer lumber, but just for the purposes of being reasonably easy, I'm saying it's all a constant density, and then you can turn the page, you see. So for your lower rail, whichever it is, you have your density and you have your width, which comes from the integration with respect to x that I've skipped over. And then you have 0 to 3/2, bottom to 1.5 inches, whichever of these it is, y squared integrate. So you do that integration. It's the top line on page 2. And you get your answer in terms of delta. So call that moment of inertia 1, which is from an axis down here at the tabletop, really just for this bottom rectangle. Then for the oriented strand board, from here up to there, you have your density and your width, and then from bottom, which see isn't 0, it's y equals 3/2, up to the base of the top rail, which is the 8. And so you work that out, and you see that's I2, and that's a lot bigger number than I1. And then for the upper rail up here, you do the same thing again. You have your density and your width, and then from the base, 8 inches to 9.5 inches, 19/2, and you do that integration, and you see I3, the 27,638 over 16. It would be times delta. So then you do your total, and you get the number you see, 237.95 times the density. And then if you compared that with 2x10 dimension lumber, which is actually, they say 2x10, but what you get is 1.5 inches by 9.5. This is the world we live in. Nothing's what it says, right? And so anyway, you see that would be a single rectangle. And so that's the same 3/2 width, and the same, supposing it's the same density. And then you do your integral 0 to 19.5 y², and you're comparing 428 and change for that with the 237 and change from the truss. So it is more, but it isn't that much more, considering the difference in cost and weight and so on. So people are certainly building their houses with stuff like this now. If you look at a house that was built, well, before World War II anyway, you're going to have the dimension lumber for your floor joists. If you have a house that was built in the 1950s or 60s probably, I'm not sure when they changed, 50s anyway, if you get under there, you're going to have you're going to have joists that are dimension lumber. And if you look at anything that's being built now, you're going to see stuff like this. Probably not as big as this one, but more like this or like that, say. And so then I also went ahead and did the comparison with 2x8. And you see, if you have 2x8 dimension lumber, your moment of inertia is less than the truss. And then for the heavier stuff, I think that's this one, I did the same sort of thing again, and your moment of inertia is 386 compared to the 237. So I think my calculations are these two, and then this one is, I didn't do, but, well, maybe I did on the, oh, yeah, I did on the back, yeah. The 5,000 pound rating, that's this one. And you can kind of just sense that this is a good deal heavier stuff. And you see, if you go through my picture and so on, you see I have 515 there. So this is a good deal stouter, as this suggests. Now, if you solve the differential equation, I have that in this handout, which is the same thing, except I've used Maple and solved the differential equation, just so you can see how the elastic curve comes out. And what we're talking about is the role of the moment of inertia in making the sag as minimum as possible. So you see I've written out the solution near the bottom of the first page, the y of x and so on. And that can be simplified. And then if you turn the pages, I've done the same kind of moment of inertia calculation. When I wrote these notes, I did the moment of inertia calculation not from the base of the figure, but assuming that the axis was in the center of the cross section as you're looking from base to top. But the people that are doing engineering and actually using moment of inertia numbers use the moment of inertia from an axis that would be at the base. So what I've gone through with you is the way that people actually do it. So my numbers that are in this second handout tell you the same relative story, that if you're comparing this, they refer to this one, the smaller of the three, and the moment of inertia for dimension lumber would be more than for this, but not a whole lot more. And you get the same relative conclusion, even though the numbers are different. But then look at the back page, and you see I've used Maple to plot the x squared times x minus 1 squared. So your second picture on the back page is your elastic curve with y positive down. The first one would be if y were positive up, but of course that's not what your load does, it sags. So you can see that there's a real sag there. Of course, you're dividing the y by the 24 times the e times the I. So then the amount of the sag doesn't look like so much, but you still have a very pronounced effect if you have this load this way. Okay, so let's look at the homework a little bit that's actually in the book. Let's see, there's nothing there. And here's, get to the point of, well, how do you do it, so to speak. If you have your book, look at problem 9, which is asking us to get the center of mass, or the centroid, for an infinite region, which you can actually do in this case as an improper integral using double integrals. So what I'm using then is x bar is x times the density integrated over the region divided by the mass. If you have uniform material, then it's x integrated over the region divided by the area. And that, in fact, is what we have in the case of problem 9. So it wants the centroid for uniform material, but an infinite region. So the area then would be the limit, since you're going off to negative infinity, from b to 0, and then the limit there as b goes to minus infinity, so off to the left. Then the top curve is e to the x, and so your first integration would be vertical from the x-axis to e to the x, and then your second iteration would be over the projection of the region on the x-axis, which is your limit from b to 0 as b goes off to the left. So your area looks like this. So you integrate dy and you have y, and 0 to e to the x. So then your integral to get the area would be the limit, because it's improper. B goes to minus infinity, b to 0, e to the x dx. Okay, your integral is e to the x. So you want the limit of e to the 0, which is 1, minus the limit of e to the b as b goes to minus infinity, and that's 0. So your area is 1. So you have this curve that extends indefinitely to the left, and the area under it is 1. Okay, then your x bar will be the integral x integrated over the region. And so first time out, you get the e to the x. So now you're talking the integral x e to the x, b to 0, left up to 0, and limit as b goes indefinitely to the left. And so if you integrate by parts, the integral of x e to the x is e to the x times x minus 1. You can integrate by parts, u is x and dv is e to the x, or you could look it up or get it out of a high-end graphing calculator if you have one, or ask Maple if you have that. And so you're going to get e to the x times x minus 1. Take the limit of that when you have evaluated between b and 0. So the upper limit, you have e to the 0 and 0 minus 1. So all that's minus 1, minus the limit of e to the b times b minus 1. Well, remember that your b is going to negative infinity, so it's like the limit of b minus 1 over e to the b, and that limit is certainly 0. It's a L'Hopital's rule type thing. Limit b goes to negative infinity, e to the b minus 1 over e to the b, and you differentiate, so on. So you get minus 1 out of this and 0 out of that. So that gets you the x bar, which is at minus 1. And then to get the quarter for y bar, you do this one. Again, your denominator is, the area is 1, so it's really just what this integral gives you. So if you do y dy, you have y square over 2, the 0 to e to the x, so you're going to have e to the x times e to the x, which is e to the 2x over 2. And then you integrate e to the 2x, and you get e to the 2x over 2. So you have this 2, and you get another 2 in the denominator when you integrate. So you have 1/4, and then this limit, which is just 1/4. So you're 1 to the left and 1/4 up. Yeah.
So you probably explained this, but I didn't catch it. I'm sorry. Is that so? Is x? Is that the balance point?
Yes. Yeah.
Okay. I guess I don't understand what the infinite region is. Then what's infinite?
Your e to the x curve is going off indefinitely to the left.
Okay.
Following the x-axis.
Okay.
But the idea is that this is so thin out here that that whole thing is offset, thinking of teeter-totter where your axis is like this, between minus 1 and 1, the products of the distances from this line of symmetry to the strips over here total as much as from this going that way.
And that is thought of as a material. Then I was thinking of that as a
you could think
okay.
of something cut out,
Okay.
cardboard, say, or
Okay.
stiff paper,
Just
that
making-
shape, and you couldn't literally go clear to negative infinity with a model, but
Sure. Yeah.
if you had a big piece of construction paper and traced the e to the x curve exactly and the axis and cut the thing out, you'd find that your balance point would not be very far from this. Since you couldn't go with your model clear to infinity, that means there'd be a little less here than there should be. So you'd have to go just a tiny bit to the left of -1, but not much, yes.
So does that function have to converge as it goes to negative?
Yeah. So
Otherwise
what,
it won't work.
but you see, your limit of e to the -x is 0 as x goes to infinity, or of e to the x is 0 as x goes to -infinity. Yeah, these improper integrals have to converge. Otherwise, you'd have to say that it is undefined.
And so, and the point of this problem is to explain that at some point it's not going to matter.
What
The
rest
material
of
on
that
the
area,
Okay.
yeah. As a practical matter, it wouldn't. I mean, if this is 1 unit across here, if you went to what would be the size of the sheet of paper, that would be far enough that you'd get your balance. It would technically be just a hair off then of -1, but you could get to where you couldn't see it.
Yeah, you're not going to get the scissors close enough to on
Yeah.
the top end of that to
Right.
get it that accurate
Yeah.
anyway. Okay.
Okay, look at problem 11. So it wants the moment of inertia relative to the x-axis down here when the density is x plus y. So the region is bounded by this line, which is y equals -x, or x equal -y, x plus y equals 0. That's a line like this, and this sideways parabola, x equals y minus y squared, which goes through 0, 0 and 0, 1. And the parabola and the line meet out here at -2 and 2. If you try it, -2 plus 2 is 0, and if you put 2 in here, you have 2 minus 4, which gives you -2 for the x. So what you want to do with your double integral is work horizontally first, because your limits are all on the slanting line at the left, and they're all on the parabola at the right. If you go vertically first, over here you'd be going line to parabola, and over here you're going parabola to parabola, which is possible, but that's a lot harder. You get into a mess that way. So you very definitely want to go, as I've shown with the green arrows, and then do the projection second on the axis you name the second, which is your y-axis, so 0 to 2. And it just asked for I sub x. So I sub x is your integral, your lever arm relative to the x-axis is y, and your moment of inertia is your second moment. So your density, your squared y dA. And the density is variable here, so you have to put that in. And that's why you have to be able to do the integration with the two variables, because you have a problem like this. So your second moment lever arm, your density, your integration, first x, then y. And so you see what I have is xy squared plus y cubed. And from here I'm going up there. And my limits And so I integrate with x, so that's x squared over 2, copy that, and then I get an x there and copy the y cubed. And then I put on my limits like this. So then I broke this into two integrals, one with this and one with that. So I put this in here, y minus y squared as x, and then I'm squaring that. This 2 is that one, and then I have the y squared. And then here I have the second part. I have the y minus y squared times y cubed down here, minus I have the minus y times y cubed. So these two are this part, and these two are this part. Okay, you follow me so far? So I have 4 pieces, because there's a term here and a term there, and my substitution for x is 2 terms here, so that gets those, and then I have 2 terms for x here, and that gets those. And of course I have the upper limit and the lower limit. So then finally, this one, when I square this out, multiply it out, square that out, and that's here, times that. So this is here. Then the orange, I have square, so that's y squared is y fourth, and the minus, that's there. And then from the putting these in this term, I have this again. Let's see. Okay, here I have the y minus y squared in there. So then this one, if you multiply these out, gets you here. This one, if you multiply those out, gets you there. And the first 2 get you here and there. So I have my 4 terms, and then I collect terms some more, and finally I have those 2 canceling, and I went in order of the powers, so I have y sixth over 2, I have a y fifth and another y fifth, so 2 of them, and then I have a 2y fourth. So now finally I put in now I have to integrate these with y. So y sixth becomes y seventh, 2 times 7, then 2y sixth over 6, and then 2y fifth over 5. And then I go 0 to 2, and I get these fractions. You notice that the 128 over 14 and the 128 over 6 reduce. And so now I have the common factor of the numerator is 64, and then I have a 7th and a minus a 3rd and a 5th, and now we're in Math 25, and we get our LCD like good boys and girls in beginning algebra, and that's 105, and finally add those up, and you get the 1 over 105 out of the denominators, and you have 64 times that. And that's what the book says it is, believe it or not. So anybody would have to say that thing gets very painstaking with all the algebra, but it's all there. So you can compute something like this, you see. So what does the moment of inertia mean? Well, that's what I was trying to address with this. It can mean something in terms of selection of what size floor joist and comparing a truss set up with dimension lumber. And you have the moment of inertia if you're talking about any kind of anything like an engine with a flywheel, and relatively by reducing the size of a flywheel, you reduce the moment of inertia, which would make the car engine wind up faster. In times past anyway, when people were taking stock things, say like Ford's, the old flathead Ford V8 of the 30s and 40s and early 50s, if you wanted to make the thing accelerate faster, you'd machine the flywheel down, among other things, because it'll wind faster the less inertia you have to overcome. So on the other hand, it becomes harder to drive because it makes it easier to kill, because you don't then have that flywheel to keep you going. In the world before automatic transmissions, people thought that the best cars were to drive were the ones where you didn't have to shift gears so many times. So they wanted something that would keep idling comparatively smoothly, even without shifting out of high gear, even at very low speeds. So especially the expensive cars of the 1930s and 40s, like the Cadillac or the Packard, or those had big, heavy flywheels. The Packards for many years had inline engines like so, and their flywheel weighed 104 pounds. Well, that's a lot of inertia to keep that thing going, ka-chugga, ka-chugga, ka-chugga. Shift, put your clutch in, please, and so on, but people didn't drive that way. Okay, so then I also have one more here. This is problem, see, I guess I didn't ever write the number. It's one of the homework problems anyway. And so you have the variable density and it wants the center of mass. This was a center of mass, but it was uniform material. So with this one, your region is outlined by this triangle. You have y equals x, and y equals 2 minus x, and the y-axis. And so it's easier if you go, as I've shown with the arrows, because they all start on y equals x, and they all end on y equals 2x. If you start the other way, down here you're going from the y-axis to y equals x, and up here you'd be going from the y-axis to 2 minus x. So reduce your work by how you go about things. So your x bar then will be your density times x integrated over the region, divided by your mass, which will be your density integrated over the region. And if you're going like this, doing y first, you're going from x to 2 minus x, as you see, and then your projection on x would be the green here, which would be 0 to 1. So this one will give you 3, and this one will give you the 8 for your mass. So you are 3/8 in, and then for your y bar, you have your density times y, and that'll give you 17 halves, and your same mass is 8, or 8 over 1, so you have 17 over 16. So you're just above the the line of symmetry of the area. Your line of symmetry of the area, of course, is here at where my stick is, going through 1, 1. But your balance point is not on that line because of this. You have a variable density. And you see, as you get up here, the y numbers get up close to 2, so they are big enough numbers that they pull the balance point up above the line of geometric symmetry. If you have uniform material, then your balance point's on every line of symmetry. If you had uniform material, your y bar would certainly be on this line that's marked with the black dots, but it's because of this that it isn't. Well, with this one, we went through all the painstaking details getting the numbers, so with this one, I'm just going to say what the numbers are. I don't care in the homework if you have a graphing calculator that'll do the integrals, or if you're using Maple or something like that, you have them set up right and then just get your machinery to give you the numbers. That's good enough. So you don't have to do all this if you've got a machine that will do it for you. But it is there if anybody wants to do it that way. Well, I think everybody sees this. So far I've received copies of the third test from 8 of the 12 people, and so what I did is I added up the 3 tests and half of your percentage on the homework scores, and where is that? If you're getting the test back anyway, I have the homework scores as Amanda has them stapled onto your sheet of paper, and so you could see where you are relative to other people. So tomorrow what we'll talk about is the triple integral with cylindrical and spherical coordinates. And the Maple that you got last week has some Maple that goes with tomorrow's class. There isn't any that goes with today's, but bring the Maple for tomorrow if you would, and we'll talk about section 15.7. So Amanda, on the strips of paper, you see Amanda, if you're doing the written homework, that's Amanda's scores, and if you're doing My Math Lab, it's the My Math Lab scores. And so I've taken half of your score rounded, so that in my total, the homework's a quarter of the total. So that you can see where you are relative to other people. So I'll see you tomorrow.